Hey, it's Rob Turner, your favorite mentor, and I'm going to go through the HVAC seminar, which I've done before. It's going to be sent to you by video because of the coronavirus. And first, I want to give you a little tour of my office. Okay, it's very messy, but we got the central area, my co-workers' offices. That's my fish tank. We have a kitchen over there and the front entrance. So let's get to the video. Okay, this seminar is about what a mechanical engineer does, the basic design activities and site visits and things like that a mechanical engineer does. It's all about the heat. You see, there's no real unit of measure for coldness. We have temperature, but when you're looking for the capacity of something, you talk about heat. We use the unit, the BTU. It talks about how much heat there is in a space. And you're going to be losing heat out of your house in the wintertime and gaining heat from the sunshine and so forth into your house in the summertime. So it's all about the heat. Talking about the BTU, I will mention the word tons of air conditioning. That's another unit that we use, and there are 12,000 BTUs in 1 ton. And by the way, 1 BTU is about the heat of a standard match. Okay, let's go to the next slide. This is bad air conditioning. We don't want an upside down fan or a fan hooked to your freezer, so we can do better than that. Let's go to the next slide. Okay, this is a slide talking about the heat loss from a house. You notice it can go out the windows, out the door, out the walls, out the roof. That's heat loss in the wintertime, and it does the opposite of that in the summertime. The heat goes through the windows and through the roof, and the people and the lights on the inside, that produces heat as well. And when you do air conditioning, you want to counteract that heat with cold air. All right, next slide. First step is to read the code book. We are in climate zone 3, and this table tells you how much insulation you have to use in your house or commercial building. For us, we usually have an attic, so we need this code book says R30, but R30 is a thickness of that pink stuff you roll out in your attic. It's usually R30 is around 9 inches thick, I think. And this chart will tell you the thickness of the insulation in your walls, under the crawl space. The code book also tells you the efficiency of windows and things like that. So you have to be familiar with the code book. Okay, next slide. When I was talking about R30 insulation, and the fact that they had increased it. In some places, they've increased it to R44, which is a lot thicker, a lot more expensive, on a new home. And this chart shows you, it's got the heat loss. Sorry, I can't point at the chart, but the heat loss, as the insulation goes down to 0, the heat loss goes to infinity, okay? But as you increase the insulation, then your heat loss goes down to a very low number. And notice that the difference between R30 and R44, it's a tiny, small difference. So you should ask yourself, is that worth the extra cost and improvement in efficiency? Maybe it is over a whole year, but I think they're going a little overboard, because at some point it's going to be a negligible difference. Anyhow, next slide. All right, I don't want you to look at all these numbers. Just try to get a gist for this. This is my load calculation program. It calculates with calculus and math, and what you do is you input the square footage of each room, square footage of the exterior wall, the square footage of the windows, the number of people, the number of computers, and all the various heat loads, and it will add it up and tell you how much cooling you need for these 5 offices. So let's go to the next slide. The grand total is 1.6 tons. So I would round up to a 2-ton heat pump unit. And these heat pumps come in half-ton sizes, like 1.5, 2-ton, 2.5, 3-ton, and so forth. So if it's 1.6, a 1.5-ton air conditioner probably won't do the job every day of the year. Even if you look at the hottest 3 weeks of the year, you're probably going to fall short. So you would round up to a 2-ton. Okay, next slide. Okay, what is an air conditioner or a heat pump? In the South, we use heat pumps because we don't really need gas heat. In the North, they use gas heat and an air conditioner. In the South, we generally use a heat pump with no gas heat. The heat pump air conditioner can heat or cool. Okay, so if you see the heat pump machine sitting outside the house, that's half of what you call a split system. And you have the outside heat pump, which is connected by refrigerant lines, and it connects to the indoor air handling unit. The indoor air handling unit makes cold air or makes hot air, and it blows it up through the ductwork, and the ductwork serves each room with a grill. So the objective is to put the right size grill and the right size ductwork and the right amount of air in each room to get the house to be comfortable and basically the same temperature in every room. Okay, next slide. That is a heat pump. It sits outside. You've probably seen them before. All right, next slide. That is a typical air handler in an attic. The silver stuff is the ductwork, and there's 2 black pipes coming out of the front of the air handler. Those are the refrigerant lines, and they go down to the condensing unit. All right, next slide. Okay, in mechanical engineering, a big part of your work is doing details. You have to draw in a very detailed manner how the contractor is going to build and install the systems. They need to know all the dimensions, the parts and pieces, and how the piping connects. And this detail talks a lot about seismic. Every piece of mechanical equipment has to be bolted down so that if there is an earthquake, it won't shake off its base and fall through the ceiling and hit you in the head. Okay, next slide. Okay, that's a thermostat. One heat pump gives you one thermostat. I want you to remember that. So if your house has one air conditioner, it's going to have one thermostat, generally speaking. And if it's two-story, do you put the thermostat upstairs or do you put it downstairs? And there's a lot of effects, comfort effects, from choosing upstairs versus downstairs. The best way to do a two-story house is to have one heat pump for the upstairs and one heat pump for the downstairs. And you'd have a thermostat upstairs and a thermostat downstairs. Okay, and we struggle a lot with providing an adequate number of thermostats with our various HVAC equipment that we put on our drawings. We'll talk more about that later. Okay, next slide. All right, this is a diagram of what's going on inside an air conditioner. It's extremely complicated, and I'll try to condense it here. So basically, you have the outside condensing unit, right? And it's got a fan. It's blowing hot air out of the top of it. Well, what it's doing is it uses a compressor and it compresses the refrigerant gas. It's a special gas to a very high pressure. And when you compress something like that, it gets hot. So the fan blows the heat off. Blows the heat. I'm talking it gets about 140 degrees. So the fan blows the heat off out of the refrigerant gas through a coil. And so then it sends that refrigerant gas to the air handler. And at the air handler, it goes through what's called an expansion valve. Well, see, this gas has had a lot of heat removed out of it. And when it goes through the expansion valve, it basically releases the pressure inside the coil, the cooling coil, in the air handler. And when it does this, it makes a phase change and it gets very cold. But the proper way to say that is it absorbs an enormous amount of heat. So when the air is moving through the air handler, through that coil, it makes the air very cold, but what it's really doing is removing the heat out of the air in your house. Okay, and then that's how the cold air comes out the other side. So after that happens, it sends the refrigerant gas through the pipes back to the condensing unit outside, and the whole process starts over again. All right, next slide. The other thing I have to do in my design work is design ductwork. This is a ductwork system I designed for a restaurant. And notice that every pipe has to be a certain size. Every grill has to be a certain size. And it has to be cover all the area and basically look nice. So that's another little piece of the puzzle. Next slide. Okay, this is rooftop equipment. These are rooftop heat pumps. those big boxes with the fans on top, blowing out of the top of them, those boxes have the condensing unit and the air handler in the same box, and the ducts go down through the roof. It's called a packaged heat pump or a packaged rooftop heat pump. Next slide. Another thing I do in my designs is the hood, the cooking hood in restaurants. These hoods draw out an enormous amount of exhaust air out of the space in the restaurant. And in addition to the hood, I have to design the makeup air, which is usually 100% outside air. Sometimes it can be cooled, pre-cooled, but you have to provide almost as much makeup air as the exhaust that's going out. Otherwise, the building would be very negative. It would suck all the air conditioning out of the building, and nobody would be comfortable. So it's called balancing the building. And that's another thing we do in HVAC design. Okay, next slide. That is the roof exhaust fan from the hood that draws the air off of the cooking, out of the cooking area and up through this exhaust fan. You can see it's coated with grease. It's not all glamorous work here. So let's go to the next slide. All right, have you ever thought about how they do air conditioning inside a submarine? You know, everybody needs air conditioning. It's in your house, your office, you know, you go almost everywhere and there's air conditioning. Well, they have to do air conditioning in submarines too. It's just something to think about. You're underwater and you gotta get rid of heat, basically. I think they can use the seawater and let the seawater absorb the heat of the air conditioners and then dump it back in the ocean. This would be a closed system. It would be separate from any of the refrigerant gas or harmful things in the ocean. But it's just something fun to think about. All right, next slide. Okay, so this is a pump. Pumps are used in another form of air conditioning called chill water air conditioning or hot water heating. And large buildings use these pumps, and they basically pump water throughout the building, and it's either hot water or cold water, and those pipes go to air conditioners in the various spaces of the large building, and the water goes through a coil in an air handler, and it absorbs the heat and makes cold air and provides air conditioning. Okay, so what makes this cold water and what makes this hot water? These are called chillers. They're gigantic air conditioners, usually on the roof or something like that, and they make the cold water for chill water systems. We have 3 chillers here serving this gigantic hotel downtown. All right, next slide. This was a picture of them lifting one of those air conditioners up to the roof. It's pretty cool. I dropped by to see that for sure. That was pretty neat. Okay, next slide. All right, the design can be extremely complicated with these chill water systems. I can't go through every detail, but you might be able to see the 2 pumps and the chillers and all the piping. It's a lot going on. This is kind of an advanced design. I just want you to just absorb a little bit of it to know how complicated things can get in air conditioning design. All right, next detail. Okay, geothermal. That's a HVAC concept that a lot of people talk about it, but I'm pretty sure most people don't know exactly what's going on. Okay, this is a basic schematic for geothermal, a geothermal system in a school. Okay, those boxes above the classrooms, those are geothermal heat pumps. They're also called water source heat pumps. They basically, instead of blowing the hot air out of the heat pump behind your house, it basically uses water to cool off its compressors, inside the air conditioner. And that water is pumped to the ground, and each well goes around 300 feet deep. And this is a closed system. It doesn't communicate with the water in the ground. It doesn't draw water out of the ground and put water back into the ground. That is another form of geothermal. It's called open system, but I don't recommend it. It's got a lot of regulations, and it can be dangerous with messing up the groundwater. So this is a closed loop system. It doesn't leak water out into the ground or draw water out of the ground, but it basically runs the water deeply into the ground and back up, and it releases heat into the ground. That's what you want to do. You want to get rid of the heat in the building. And when the water comes back up, it goes back to the air conditioners in the school, in the geothermal school, and it cools off their compressors again. Then the water turns hot, you pump it down to the wells, it goes through the wells, and it releases that heat. That's how it works. Simple as that. Okay, so next slide. When you design geothermal, you look at a map like this, and you notice in Charleston, it shows 67. That means the average ground temperature is under the ground is 67 degrees. So your hot water that's coming from the air conditioning that's going down into the geothermal wells, that water can be over 100 degrees, maybe 110. When it goes in a 67 degree ground, that's a big temperature difference. It gets rid of a lot of heat, and when the water comes back, so that's basically how that part of it works. All right, for a school, next slide. For a school, it needs a lot of wells. As you can see, that's the football field behind the school, and each one of those dots is a well, 300 feet deep, and they're all connected with piping, and it goes back to the main mechanical room in the school. Okay, next slide. Remember when I discussed one heat pump gives you one thermostat? Well, in an office with 200 people in there and 200 different offices, you can't ask them to share a thermostat between 50 people. Most people everybody wants a thermostat in their office. Well, that would be pretty expensive to do a tiny heat pump air conditioning system for each office. You'd have 200 condensing units on the roof, and it'd be extremely expensive. This concept is called a VAV system. It gives you as many thermostats as you want. So basically you have a big central air conditioner shown at the bottom of the picture. This air conditioner basically makes a large amount of cold air. Okay, so it serves the cold air to the various floors of the office building. But at each office or each office area, it goes through what's called a VAV box. And this VAV box has a damper in it, and the damper is connected to a thermostat. So when the thermostat says I'm hot, the damper opens and lets more cold air out. When it says I'm cold, the damper closes. The VAV box also has a heater coil in it because the air conditioner is only making cold air. So whenever you do need a little bit of heat, the heater coil will turn on. And by the way, in an office, you rarely ever need heat because there's computers, copier machines, lots of people, lights all over. It's making a lot of heat. And even in the wintertime, you're most likely going to be running the air conditioner. All right, so in this design, a VAV box is very inexpensive. And each VAV box gets its own thermostat. So you could have 100 thermostats in this building if you wanted, and it wouldn't be that expensive. So that's another concept that we have to choose from in HVAC design. All right, next slide. This next slide is a design I did for a large office building with a VAV system. I can't go through every detail, but I wanted you to get a feel for it. You know, the mass in the center of the drawing is the central air conditioner, and you can see ductwork is coming out of it from all sides, and then it circles around the office area. This drawing doesn't show where all the cubicles go, and this drawing is just showing where the VAV boxes are and the typical routing of ductwork that could be installed once they find out where their offices and where their cubicles go in this space. Okay, next slide. All right, here's another drawing that I typically do. This is for a school. This is a floor plan, and it shows the gymnasium, and you can see the purple ductwork going across the ceiling of the gymnasium. As you can see down at the bottom, it's very busy. There's the locker rooms, and that's where the big air conditioner is above the locker rooms. And so, you know, like I said, we have to draw this stuff so that somebody can build it. So let's go to the next slide. This is a section view of that same design. And it shows the contractor where the duct goes, how high it is, you know, and this is a section view that gives him another view, he or she being the contractor, another view of how to build this air conditioning system. So it's a lot of detail. You gotta think about space and how high stuff is. Will it fit? You know, you have to draw it so somebody can build it. All right, final slide. That's me with no beard in the middle, showing these guys all about my drawings. And they're very, very interested. So if you have any questions, please send them to me. Take care, everybody.